In this video, I introduce how to compute the volume of a solid revolution by using what's called the shell method. Now, the method of washers is not always the greatest thing to use. For example, suppose you have a positive function and you want to define a region to be below that particular graph, above the x-axis, and between the lines x equals a and x equals b. For example, I've given you one here. Well, the method of washers might be pretty awkward to use in this case. Consider this one rectangle. As that rectangle goes and moves up and down as the y value changes, notice that we'll be forced to use 3 integrals. We'll have to break that region up into 3 different spaces and do basically the method of washers 3 times. That sounds terrible. 3 different integrals? Terrible. Also, the rectangle is defined mainly by its leftmost and rightmost x value. That means in some of these cases, I'm going to have to take the equation y equals f of x. I'm going to have to solve for x, and that might be beyond my algebra skill. So, you might notice though, the main problem we're having is that the representative element, our rectangle, is perpendicular to the axis that we're rotating around. Let's just not do that. And instead, let's pretend that the rectangle is parallel to it and have it revolve around the axis of rotation instead, and try to compute the volume that way. We just won't be using disks and we won't be using washers anymore, because the volume that that representative element will generate is more like a shell. To come up with a formula for how to find volumes by using shells, let's take the interval from a to b and partition it into x0, x1, so on up to xn, where we start at a and end at b. Now, if you look at the kth such interval, as I've highlighted here, I can pick any x value in that interval when I make my Riemann sum. I'm going to pick, though, for convenience, the midpoint between those 2 x values. I'll just call that c sub k. That will then generate 2 points, one on the function's graph and one on the x-axis, and that gives me a height that you see here in red. Also, of course, there's a difference in those x values in the partition. That gives me a thickness. So with the height and the length, that makes a rectangle. Just do this for every single subinterval that we generate. I'm going to highlight only one of them though. Now that I have that, why don't we take this picture in 3 dimensions and let's take that rectangle and let's just rotate it. When you do so, you wind up getting a bunch of shells like this. I'm going to find the volume of that shell, add them all up, and then in the limit, find out what the volume should be. But first, we need to figure out a way to find the volume of that shell. So it's just 2 cylinders where you take a larger radius and a smaller radius and then just subtract those different volumes. So the 2 radii is large V and large radius and small radius, capital R and lowercase r. And the height of my shell in each of them is going to be h. So the volume then is just the difference in those 2 different volumes of cylinders. Now that formula though is not convenient, so let's just manipulate it a little bit. Notice there's a common factor of pi and h, and also the resulting r squared minus lowercase r squared can be factored also. So I go through the process of factoring the first 2 terms, and then I factor the capital R squared and the minus r squared. Also though, at the same time, I multiply and divide by 2, for reasons you'll see in a minute. Because then I have capital R plus little r divided by 2. That's the average of the radii. And then you have capital R minus r. That winds up being the thickness of the shell that we have. So we see that the volume of the shell should be 2 pi times the average radius times the height of it times the thickness of that shell. Now that we have that, let's go back to the original picture. Here's what we had before: the partition, the choices of x, the choice of c sub k inside that interval, the rectangle, the height, and so on. We know how to find the volume of the shell. All we have to do now is put in the simples. So the average radius, well, that's what c sub k is, right? That's the midpoint. That's why I picked it, because it was going around the y-axis, and x values are distances from y-axis. The height, well, that's just the length of that red segment, and that's the function at c sub k, that's one y value, minus the value of 0. So that height is just f at c sub k. And the thickness, that's just the thickness of the rectangle. So that will then be the change of x sub k. So my volume generated from that one little rectangle as it rotates around and creates a shell is given by this formula. So the overall volume is about equal to the sum of these little volumes, and that creates for us a Riemann sum. Since we know that x times f of x, at least we're assuming, is continuous, then we know then the limit of these Riemann sums of this type as the norm goes to 0 should exist and in fact equals, by definition, the definite integral from a to b of 2 times pi times x, where x represents the average radius to the actual axis, times the function value, that represents the height, times dx, that represents the thickness. So let's do an example. Let's find the volume of the region as it rotates around the y-axis if that region is bounded in the first quadrant and the graphs of y equals x squared and x equals 4. Now I did this exact same thing, but before I went around the x-axis as an example of using the method of disks. Since going around the y-axis, I actually did that one too. I had to use the method of washers and it wasn't terribly nice looking. So let's just do it this way. Hopefully it'll be simpler. So to do that, since I'm going around this axis, that means my representative element, my rectangle, is going to be parallel to that axis. It's going to move left and right with a changing x value. The interval is going to go from here to here. So I'll need to know what those x values are in order to figure out the bounds. And I'll need to know this point and that point. Now notice, as the rectangle moves left and right, those 2 points stay on their curve, so I only ever need one expression for the height of this rectangle. Now the height then would wind up being a difference in 2 function values. The top function, this would be given by its y-coordinate, that's x squared, and this y value is, of course, 0. So the height is then x squared minus 0, which is just x squared. Now the radius, that's the distance from the center of the rectangle to the axis, and that distance is just, well, x. It's x minus 0. It's this x value minus this x value. So that would then be, of course, just x. Well, the range of x values is 0, and we know this is where this last point is on the line, x equals 4, so we know that's 4. So the integration should then be, the volume is from 0 to 4, the volume equals the integration from 0 to 4 of 2 times pi times the radius, which here is x, times the height, which is x squared dx, and that's it. So this is going to be the integration from 0 to 4 of 2 times pi times x cubed dx. And if you compare this integral to when I did it using the method of washers, I think you'll agree this is a lot simpler. And in fact, I'll leave it for you, because I'm sure you can do it. Let's try that again. This time the region is bounded by the graphs of y minus x equals 2 and x equals y squared. It's going to be revolved around the line y equals 2. Notice it's not the axes, but that's okay. The idea is exactly the same. I want to use the method of shells to find the volume of the solid. Now the first thing you should ask is why should I use the method of shells and not the method of washers? If I use the method of washers, I'd be forced to go and use a rectangle that is perpendicular to the axis. But to do that, notice that this point, as this rectangle moves left and right, would always stay on the same curve, and therefore its description, x as a function of y, or y, in this case, y as a function of x, would never actually change. But this point, though, actually does undergo a radical definition change right at this point. Because of that, I would need to do this problem twice if I use the method of washers. I'd have to do the problem once in this region, and I'd have to do it again in that region. And I just don't feel like doing that. So let's just go ahead and erase that whole thing. And instead, let's now use the method of shell. So I need a representative element that is going to be a rectangle in this case, and it's parallel to the axis of rotation. It will move up and down with respect to the changing y value, and I'm going to need the distance from the axis to the center of that rectangle. That's my radius. So I'll need to know then, was this y value? Well, clearly, that's just 2. So the radius is the larger y value minus the smaller one. There you go, that's the radius. Now we need to know what is the height. To do that, I need to know this x value, and I need to know that x value. So the leftmost x value is easy to find. It's just y squared, because that point is always on the graph, x equals y squared. The rightmost point is always on the graph, y minus x equals 2. So I just need to go and solve this thing for x to get x is equal to y minus 2. I would then find the height to be, it's the larger x value minus the smaller x value. So that then gives me a just y minus 2 minus y squared. All right, great. So the next thing I need to do is I need to know how much that this y value is allowed to vary, because I picked this y value and I let that y value is what allows the rectangle to move up and down. Well, to find those particular y values, one thing you could do is you could just find this point of intersection. You could then find this point of intersection. That would then give you the two different y values. So you could just set these equations equal to each other and find out what y would equal to. Although I'll just cheat, because if you look at the picture here, I've drawn it to scale, and it looks like it goes from -1 to 2. So the volume then is equal to the integration from -1 to 2 of 2 times pi times the radius times the height dy. That's it. And that integral is easy enough to do. You just distribute the particular product to turn it into a sum or difference of constant multiples of things you know how to integrate. You then integrate each piece. That's it. Once again, this is simple enough. I'll leave it to you. And that gives you a basic introduction to the shell method. Yes, the problems can become more complicated, but not really much more. Both the shell method and the disc and washer method, and really the method of using similar cross sections, it boils down to a lot of, can you draw the picture? Because if you can't draw the picture, you really have no shot of setting these things up. You'll notice that a lot of the problems to, in the end, give you integrals that are not that difficult. We will handle the more difficult integrals in the future. This is just to get you started.